Very well, future secondary educators. Let's set up our in-class activity. Let's talk about how to visualize solids and break them down to approximate them using shapes that we're used to. As the weather gets warmer, we start thinking about summer shapes. And when we think about summer shapes, we think about the ice cream cone. How does the ice cream cone break down? You're like, I don't care, just give me some. Well, it looks like this is some sort of semicircle, and this is some sort of triangle. And what happens when we spin those around an axis of rotation? Well, the top part is a well, it's a semicircle spun around. It's a hemisphere. It's a hemisphere. And we know that the volume of a sphere is 4/3 pi r cubed. So the volume of a hemisphere is 2/3 pi r cubed, where that's r. So we would need some way to estimate what that r value is. Either in the picture or from context or with a ruler or you name it, we would need a way to estimate what that radius is. Then the bottom part, what happens when you take a triangle and spin it around an axis of rotation? Well, you get a cone, and that cone has a base radius, which is conveniently the same as the hemisphere's radius, and you get a height. And you would have to estimate what that height is based on the picture or context or your knowledge of ice cream cones or something. How much ice cream is in this ice cream cone? It's the hemisphere plus the cone. And how do we find the volume of a cone? It's 1/3 area of the base times the height. So this is a normal thing for us to teach teenagers how to do. It is perfectly normal for us to teach teenagers how to break a shape down into two other shapes that approximate the real thing. They're not the real thing, but they approximate the real thing. A wise friend of mine once said, I can give you an exact answer to an approximate problem, or I can give you an approximate answer to the exact problem, but I can't give you the exact answer to the exact problem. And that wisdom is probably fair here. Well, in a different context, let's imagine that you're looking to approximate the volume of a house. Your heating and cooling system, the size of your heating and cooling system is based on the size of the house. What's the volume of the house? How do you approximate the volume of the house? Well, this house appears to be fairly straightforward. There appears to be a top part, and there appears to be a bottom part, and the bottom part is definitely a rectangular prism. So we would need to know what this length is, and what this width is, and what that height is, because the volume of a rectangular prism is length times width times height, right? And as long as we have good approximations for length and width and height, we can find the volume of the first floor of the house. The top floor, that's another ball game. That appears to be a triangular prism, right? That appears to be a triangular prism. And a triangular prism, you just need, well, you need roughly the same things, don't you? You need the width of the house and the height of the triangle and the length of the triangle. I'm sorry, the length of the prism, because the volume of the triangular prism is the area of this base, right? 1/2 area of the base times this distance, which happens to be the same L as before. In fact, this W is the same W as before. This height is not necessarily the same. This height is not necessarily the same as that height, right? this height is not necessarily the same as that height, but those L's and W's agree. So if either by the picture or by context or because we actually physically measured, we can approximate the volume of the house by putting two shapes together. You can do it with trees. It's easier to find the volume of a cylinder or the volume of a cone or the volume of a sphere than it is to take an oval and spin it around in 3 dimensions. This is probably some more calculus type stuff. This is definitely some calculus type stuff, but you can teach teenagers how to find the volume of a cylinder, and you can teach teenagers how to find the volume of a cone, and there's a cylinder underneath, there's a cylinder underneath, there's a cylinder underneath. You can teach teenagers how to find the volume of a sphere. So you can make questions for teenagers that ask them to do this sort of thing. And you can get pictures from a wide variety of places. Bing and Google are my favorites. All of that sets them up to do this sort of thing. And this is, I'm told, a standard 4-point question on a New York State Geometry Regents exam right about now. This is the iconic quintessential one. This is the dreaded water tower question from a few years back. That's a water tower from some town. They took a picture of it, and then they approximated that with a cone on top of a cylinder on top of a hemisphere. And they gave the kids some dimensions, and basically they had to figure out the volume of the water tower. It is this sort of skill that young people need to do those questions. And so it is this sort of skill that we have to teach them, going from things that are a little bit more straightforward, from things that are a little bit more straightforward, from things that are a little bit more straightforward. We want them to be able to get to a place where they can take a very complex shape and break it down into approximating shapes whose volumes we know how to find. So as we are scaffolding things together for teenagers, we want them to build toward this kind of a conceptual problem. Okay? That sets us up for our in-class activity this week. I am looking forward to seeing you when we gather. All my best until then.